Welcome back. In this video, I'm going to solve exercises 1 to 5 of chapter 3 about compactness. In exercise 1, we have to show by going back to the definition that a finite union of compact subsets of a space X is compact. So it's enough to prove that for the union of two compact subspaces or subsets, because the general result follows by induction on the number of these sets. So since this is a direct application of the definition, I suggest that you take a paper and a pen and try to prove that on your own before you see the solution. And you can do the same thing for all the remaining exercises. Okay, so let K1 and K2 be two compact subsets or subspaces of the topological space X. We have to prove that every covering of K1 union K2 by open subsets of X contains a finite subcovering. So consider an arbitrary covering of K1 union K2 by open subsets of X. What does this mean? It means that every O lambda is open in X, and the union of O lambda contains K1 union K2, and therefore the union contains both K1 and K2. Therefore, O lambda is a covering of K1 by open subsets of X, and compactness of K1 tells me that I can extract from this covering a finite subcovering, O lambda lambda in L1, where L1 is a finite set of indices. And similarly, since O lambda is a covering of K2 by open subsets of X, I can extract another finite subcovering that I call O lambda lambda in L2, where L2 is finite. Therefore, when I put together these two finite subcoverings, I get a covering O lambda lambda in L1 union L2, which is finite because it's a union of two finite collections. So, and it covers K1 union K2, and that's it. So this means that K1 union K2 is compact according to the definition. Okay, exercise 2, less trivial. We have in a metric space X a decreasing sequence of non-empty compact sets Kn. So decreasing means that K1 contains K2, K2 contains K3, and so on. And you are interested in the intersection. Now, of course, I know that the intersection is not empty. Why? Because since Kn is compact in X, Kn is closed. And therefore, since Kn is not empty, the collection Kn has the finite intersection property, and therefore the whole intersection is not empty. Okay, but now we have to prove that if U is an open subset of X that contains the intersection, then it contains Kn for all n large enough. Okay, so since the sequence is decreasing, it's enough to prove that U contains some Km. Yeah, because if it contains Km, it contains Km plus 1 and Km plus 2 and so on. So we reason by contradiction. If U does not contain any Kn, it means that Kn intersects the complement of U. Okay. So what does it mean that Kn is not in U? It means that there exists an element in Kn not in U, so it's in the intersection. And this is true for every n. Now, if U is open, the complement of U by definition is closed. And Kn is closed because it's a subset of a metric space. Therefore, the intersection is closed. And this, if you call Fn this intersection, then Fn is a closed subset of X. And therefore, actually, Fn is a closed subset of K1, is a closed subset of K1, which is compact. Okay? So everything is happening here in the compact set K1. And according to a corollary of the lectures, the whole intersection should be not empty, okay? Because it's a decreasing sequence of closed sets which are not empty. So the whole intersection must be not empty. Okay. Now X need not be compact, but this intersection lives in the compact space K1. So the whole intersection should be not empty. But if I write the intersection by the distributivity laws, this is just the intersection of Kn intersected with the complement of U. So it's just K intersected with the complement of U. Okay? But this is empty because U contains K. And therefore it's a contradiction. Therefore, U contains some Km, and therefore contains all Kn starting from M. Okay, so this concludes exercise 2. Now, the result is not true without the assumption of compactness. Try to construct a counterexample. Exercise 3 is an exercise about the projections. So we have here two metric spaces x and y, and we equip x times y with the product topology or with any of the distances that we discussed in chapter 1. So we can equate with the distance d1 of xy is the distance between x1, x2, and plus y1, y2. But the distance is not relevant here. All that we need to know about this topology on the product is that if a sequence xn, yn in the product converges to xy, then each component converges to the corresponding component. This is all, and this is something that we expect. Okay. Now, we remarked in a previous exercise that we proved that pi1 is continuous, actually, in the lectures. And we mentioned that pi1 need not be a closed map. Closed map is a map that transforms closed sets into closed sets. And this is something different from continuity. Because continuity involves the inverse images of closed sets. So map is continuous if the inverse image of a closed set is closed. But here we are talking about the direct image. So please don't confuse the direct image with the inverse image. Okay, but here we have an extra assumption. Y is compact. And under this assumption, we have to prove that the projection onto X maps a closed set into a closed set. Okay, so we consider a closed set A of X times Y, and we have to prove that its image under pi1 is closed as well. Now, how do we prove that a set is closed? We have two strategies. Either that we prove that it's equal to its closure, or we prove that the complement is open. Let us follow the first strategy. So, how do I prove that pi1 of A, the closure of pi1 of A is contained in pi1 of A? Because pi1 of A is always contained in its closure, so it's enough to prove that the closure is contained in pi1 of A. So we take an arbitrary element x in the closure of pi1 of A. And of course, this set lives in X. So, and we must prove that X isn't pi1 of A. Okay. Now, by proposition 1.8, since we are dealing with metric spaces, there is a sequence xn in pi1 of A that converges to X. This is according to proposition 1.8. Now, what does it mean to say that xn is in pi1 of A? By definition of the direct image, it means that xn is the image of some element in A, and A is a subset of the product. So xn is the image of some couple, and the first component of the couple must be xn, because if xn is pi1 of zn yn, let us say, then necessarily zn is equal to xn. So therefore, there is a sequence yn in capital Y such that xn is the projection, the first projection of xn yn. Now, compactness of Y, which is equivalent to sequential compactness, tells me that yn has a subsequence, ynk, that converges to some y. By definition, xn converges to x. Therefore, any subsequence of xn also converges to x. So, in particular, xnk converges to x. So, this is all what we need to know about the product topology, that if xnk converges to x and ynk converges to y, then the couple xnk, ynk converges to xy in the product topology. So we have now a sequence xnk, ynk in A that converges. So the limit must be in A bar, but A is closed, therefore the limit is in A. And that's it. So it means that pi1 of xy is in pi1 of A, but pi1 of xy is just x. So x is in pi1 of A. So we started with an arbitrary element in the closure of pi1 of A, and we proved that it is in pi1 of A. So this means that pi1 of A bar is contained in pi1 of A, and therefore we have equality, and therefore pi1 of A is closed. Okay. So this concludes exercise 3. Exercise 4, we encountered such a similar exercise in chapter 2 when we proved that if a function is continuous, then its graph is a closed set in the product. Here we have to prove the converse, but we have an extra assumption that the set Y is compact, the space Y is compact. Okay. Now, there are several equivalent conditions to continuity of F, and this was recorded in proposition 2.1. So please go back to this definition. So I have to prove that F is continuous at every point X. And for this, it's enough to prove that if Xn is a sequence converging to X, then there exists a subsequence, X and K, whose image under F converges to F of X. And this was the last property in proposition 2.1. So we start with a sequence Xn of the first space, of the source space X, that converges to X. Now, the image of Xn under F is a sequence in the space Y. And since Y is compact, it is sequentially compact because it's a metric space. Therefore, the sequence F of Xn contains a subsequence which is necessary of the form F of X and K that converges to some Y. Okay. Therefore, the couple X and K, F of X and K, converges to the couple XY. Because Xn converges to X, therefore any subsequence of Xn converges to. So the couple X and K, F of X and K converges to XY. So the limit, now X and K, F of X and K is a sequence of the graph. Therefore the limit must be in the closure of the graph. But since the graph is closed, the limit is in the graph. What does it mean to say that XY is in the graph? By definition of the graph, it means that the second component is the image of the first component under F. So Y is equal to F of X. But by construction, F of X and K converges to Y. Therefore, F of X and K converges to F of X. Therefore, we started from an arbitrary sequence Xn converging to X, and we found a subsequence X and K whose image under F converges to F of X. And by proposition 2.1, this means that F is continuous at X. And since X was arbitrary, this means that F is continuous everywhere. Okay. And we observed that the conclusion is not true if we remove the assumption of compactness. Okay, we gave a counterexample in the previous chapter. Here we have an extra assumption of compactness. So this concludes exercise 4. Last exercise, we have two subsets. For any two subsets, capital A and capital B of Rn, we define the sum of the two sets in an expected way. So what is the sum of two sets, A and B? It's by definition the set of points in Rn of the form x plus y, where the first term is in A and the second term is in B. Okay, so first question, we have to show that if A and B are compact, then this new set, their sum, is also compact. And in the second question, we have to show that if one of them is closed and the other is compact, then the sum is closed. So let us prove the first point. Here I will present two methods. One involving continuous functions and the other involves sequences and subsequences. So if we consider the function capital L of two variables, so from Rn times Rn into Rn, that to each couple associates the sum of the components. Now, it's easy to see that this map from Rn times Rn into Rn is continuous, trivially, because it's the sum of two continuous functions. So the first x is just the projection, and the projection is continuous. Therefore, if you denote this map by L, L is continuous. But by definition of A plus B, we see that A plus B is just the image under L of the product of A times B. But since A and B are compact, we know from the lectures that the product is compact. And the direct image, once again, the direct image of a compact set under a continuous map is compact. So compactness is conserved under continuity. Therefore, L of A times B, which is A plus B, is compact. Okay? So this is the first method. Second method, we show that A plus B is sequentially compact. So we take an arbitrary sequence xn of a plus b, and we prove that it has a subsequence that converges to an element in a plus b. So since xn is an a plus b, then by definition, xn is the sum of two elements. The first one is in a, the second one is in b. So I can write xn equal an plus bn, where an is in a and bn is in b. So therefore, we have two sequences now, an in capital A and bn in capital B. Compactness of A, or sequential compactness of A, tells me that an has a subsequence a and k that converges to some point A in capital A. Now, if you consider the sequence B and K in B, since B is compact, B and K has a further subsequence that I may still denote by the same symbol that converges to some B in B. Okay, this is a practice used often in analysis and topology when we don't want to overload with subscripts. So here it should be B and KL. Okay. So, but in order to avoid subscripts, we may still denote the subsequence by the same symbol. So now what do I have? I have A and K converges to A, and B and K converges to B. Therefore, X and K, so A and K plus B and K, which is X and K, converges to A plus B. Okay. Therefore, we found a subsequence. Actually, it's a subsequence of a subsequence, but so therefore it's a subsequence. So we found a subsequence of xn that converges to an element in A plus B, and this means that A plus B is sequentially compact, and therefore compact. Second question, we have to show that A plus B is closed, and here again we have two strategies. Since we are dealing with closed sets, it's better to prove that the closure of A plus B is equal to A plus B, or is contained in A plus B. So we take an arbitrary element in the closure of A plus B, and we prove that it is in A plus B. So again, by proposition 1.8, we have a sequence xn in A plus B that converges to X. Therefore, and since xn is in A plus B, therefore we can split it into the sum of two sequences, one in A, the second in B, as we did. And now we assumed here that B is compact. So the sequence Bn has a subsequence Bnk that converges to some element small b in capital B. So what do we have now? Bnk is convergent. X and K, xn is convergent to X, and therefore X and K in particular converges to X. So A and K, which is X and K minus B and K, converge to what? To X minus B. And I call this element small a. I don't know yet that A is in capital A, but it will be in A. Okay, so A and K converges to X minus B, and I call this F. Now, why A belongs to A bar? To A, because A is closed. Okay, so the limit must be in A bar, and since A is closed, A is in capital A. So therefore, I can write X equal A plus B, where small a is now in capital A and B is in capital B. And therefore, X is in capital A plus capital B. So we proved that the closure of A plus B is contained in A plus B, and therefore we have equality, and therefore A plus B is closed. So this is a typical reasoning in analysis and topology. So this concludes this first part of the exercises of chapter 3. Thank you for your attention, and in the next video I'm going to solve the remaining exercises.